It's complicated, and unfortunately I was not able to explain it properly. You know, I always gave it in Hungarian. In Hungarian the subscripts are different because spring is rugo in Hungarian. We use R for that and so on. And for example, I run into a problem that when I speak about sensed and spring, they both have the subscript S. And I try to do that. I don't give any subscript for the sensed values, which are measured, okay? But I gave the subscript S for the spring, okay? So anyway, that's why this part might be a little bit messy. But now I try to rewrite it again, this second control strategy, okay? But we will actually now digitize. So what we are going to do now is the digital force control, okay? So I will write here the digital version, but when in the model, what you can see there, the left side, the PD stuff, these are all digitized, okay? And I will use the second strategy, so I will use this one, okay? And these are all digitized. So we have to use the sampling there, okay? And so it will be mass times acceleration, control force. The control force has three terms, the P, the D, and we add the sensed force, the spring force, and the Coulomb friction. Now the force error, it is the measured position K multiplied by the stiffness minus the desired force, okay? Then its derivative is K times Q dot. Sorry about this, I just try to represent that this is the force error, this is the force error derivative, and this is the measured force, the sensed force, okay? And this is the real spring. Now what will happen, you know, that these ones, which I denote by red, okay, here, these values are measured. So these will be digitized, okay? These are digital and sampled, okay? But this one is a real spring force, it is not. And also the acceleration is not. So because this is the real world, okay? This is continuous, this is discrete. Okay, everything else is discrete and digital. So that's why these terms must be written in a digital way. And also the Coulomb friction is in real time. It's real, it's not digitized. So then if you try to put it together, it will be mass times Q double dot T, okay? And then this term can be put on that side, so it will be plus K times QT. So actually there will be a real oscillator, okay? On the right side, we will have these discrete things, so it will be minus P times K times Q at Tj minus tau. But we also have one here. I'm sorry. So these two will be combined, and actually it will be 1 minus P. Let me check. I don't want to. Yes, it will be 1 minus P. So it will be 1 minus P times K times Q at Tj minus tau. Okay? This is which comes from the sampling. This is the minus P times, and this is the plus 1. Okay? So it will be like this. Then there will be the differential gain minus D times K times Q dot at Tj minus tau. And then I had everything, and at the very end we have the minus C times the sine of Q dot T. Okay? That's it. And this is valid for T, Tj plus tau. Okay? So this is I don't present the figure again, but you remember that we have the signals, we measure it, and then this piecewise constant forces are given. Okay? So from the original Q, we do this, and then the piecewise constant values are here on the right-hand side. Okay? Now, let's check whether the equilibrium, the desired position, is right or not. Okay? Oops. The P times Fd, I forgot about this, P times Fd, okay? I have to put it also here, plus P times Fd, okay? I'm sorry. It's also there. Plus P times Fd, okay? It's here, plus P times Fd. Otherwise, we wouldn't get the right result, okay? Because now, if I try to figure out the trivial solution, okay, when C is equal to 0, then trivial solution, which is the equilibrium, okay, equilibrium, then Q will be constant. If Q is constant, then it will be, the derivative is 0, so that will be Q equals to, it is constant, and the sample value is also constant, okay? So it will be 1 minus P times Q times K times Q. This will be 0 because the derivative constant is 0, and there will be a plus P times F desired, okay? And I forgot about the K here, sorry. K times Q. Okay, then K times Q will cancel, and I must obtain that from this Q is equal to Fd over K. Yeah, that's correct. Which is actually Q desired. Okay, so it was just a check that our equation, even in the digitized form, it's okay, because still the trivial solution is the desired position, okay, where we want to be, okay? And again, if you want to check that if C is larger than 0, then how much is the position error, okay? Then what we have to do is the same, just at the end we have to add the C, okay? And if we add the C at the end, it will be C over all the other stuff, and since K times Q will cancel, it will be only C over K times P. Okay, C over K times P, from which the force error is C over P. So again, even in the digital form, the equation looks all right. Okay, but now it's high time to get rid of this stupid Q, because its equilibrium is not at 0, but at QD. So now we will introduce a new coordinate, okay? And this will be denoted by x. And this coordinate x will be taken here, okay? This will be x. And it will have the 0 position when Q is equal to QD, okay? So now we will say that, all right, let's transform it or linearize around Q equals to QT. So new coordinate x is the perturbation around or about QD. So this will mean that I will say that Q of t is equal to QD plus x of t, okay? So it's the usual way as we do the linearization, which will mean also that Q dot t will be the same as x dot t, okay? And then, and Q double dot t will be the same as mx double dot t. So then our equation will be m times x double dot t plus k times qd plus k times xt, okay? I just substituted there qd plus xt instead of q, equals to 1 minus p times k times The sampled value of this starts with QD. Then there will be also a plus 1 minus P times K times the sampled value of x at Tj minus tau. Is it okay? So here instead of that, I substituted these two. Then I will continue it with minus d times k times q dot is the same as x dot at Tj minus tau, okay? Then there will be the plus p times fd, okay? And the minus the c times the sine of x dot t, because q dot t and x dot t is the same. So it's a bit lengthy, but now there will be a big simplification, because k times q dot will cancel with this one, okay? This minus p times k times q dot, this one, will cancel with p times fd, okay? So we could get rid of these terms, okay? Also, still we have the same error, because if we want to calculate delta from this, it will be c over k, k times x will cancel c over p. So it's again still the same, c over k times p, and delta f is still c over p. So again, it was just a check that we did it correctly. These terms will cancel, and now we will get, finally we will get the final form, and from stability viewpoint, we will neglect this c, and then we will just try to solve it in the way. So for the stability investigation of xt identical to 0, okay? That's which will be analyzed. Is analyzed with, and now let's put it down, and I will put it into a frame, okay? I will check it in my lecture notes whether I did it correctly, but I hope it will be all right now. M times x double dot t plus k times xt equals to 1 minus p times k times x at Tj minus tau minus d times k times x dot at Tj minus tau. And that's it, okay? So, yeah, let's see it again. X double dot and k times 1 minus p. Yeah. Moreover, we will simplify it even further, even before we introduce the dimensionless variables, because the first thing is that also in Craig's book, and anybody who did experiments already with force control, what they experience is that the differential gain messes up everything. So it is simply said that don't use differential gain. For the first glance, it seems to be unreasonable, because as we already discussed it during the break, if there is no differential gain, the orthogonal strategy wouldn't stop. It would just go and start vibrating around QD, okay? And it wouldn't like to stop. So we need the differential gain to stop it. Still, it's not explained properly. They just say that the practical experiments show that it's better not to use differential gain. But then how will it stabilize? The fun thing will be that the time delay will stabilize it. So actually, the sampling will be good. And this will work in a positive way, which is absolutely surprising for the first glance, but since nobody does this calculation, they just don't know about it, why it happens. So it's a practical suggestion, or practical observation, or I don't know how to say it. Don't use differential gain. So choose d equals to 0. Let it be 0, okay? For the first glance, this practical observation or practical suggestion is unreasonable. How it will be damped? Well, of course, you can always say that, well, maybe the motor characteristics will give some damping, or in the spring there is an additional damping, or they put there some damping, so maybe some physical damping may help. Physical damping or DC motor characteristics. Okay, so there may be several reasons why it happened, but we will show that actually the sampling will damp. It's very funny. On the other hand, we will give a more precise explanation, will come later, okay? Mathematical. That was actually that guy whom I showed you in the experiments, who just pulled up and down that robot. That was in his PhD, that he analyzed it very deeply, that what happens if we add D. The funny thing is that actually if we add this, the situation gets mainly worse, okay? That's very funny. It destabilizes the system. But it's very lengthy because the guy wrote a whole PhD on that, so I will not explain the details, but it will be reasonable, so you will see that it works. So we will make it even simpler. We will neglect this term also, okay? And then, of course, we will also divide everything by the mass m, okay? So finally, the equation what we will investigate will be something like this. X double dot t plus omega squared times xt, because k over m is omega squared, is equal to 1 minus p times omega squared times x at tj minus tau, where t is in the interval tj plus tau. Okay? So I will try to put it into a frame, or maybe even not, because then I will make it dimensionless. But it's already an important equation, okay? And that's the one we will start analyzing, where omega equals to the square root of k over m is the natural angular frequency of the uncontrolled system, okay? So if there is no control of the uncontrolled system, uncontrolled system. So when there is no control in the system, we drop this whole thing away, okay? All this thing we drop away, and then it just oscillates by itself, okay? Then this would be the natural frequency, okay? Good. Dimensionless time. So the same procedure as we did. Capital T, T over tau, dimensionless, okay? And actually, we don't have to introduce a new gain, because the proportional gain itself is dimensionless. So that was okay, we didn't have to introduce it. And again, I will denote by y dot denotes d over dt. It will be 1 over tau times differentiation with respect to the dimensionless time. So I will multiply the whole thing with tau squared, okay? And then it will be x double prime capital T plus omega squared tau squared, or you can even say omega times tau squared, but anyway, as you like it, write better. Xt equals to 1 minus p times omega times, maybe I will write it as omega times tau squared. Okay? Omega times tau squared times x at j minus 1, okay? And then the dimensionless time varies between j and j plus 1, okay? So actually this will be the even better form, the dimensionless form. And you see, the investigation will be done in the plane of 2 parameters only. 2 dimensionless parameters left. Actually, we could make it 2 because we got rid of d. We just dropped away the differential gain, okay? And that's why we are left with 2 parameters only. One is, of course, the p, okay, the gain. The other one is omega times tau. And it's dimensionless because it's 1/2 times second. You could also write it as omega is the 2 pi times the natural frequency. Now I will put an n for the natural frequency, okay? Because later there will be the real vibration frequency and I don't want to mess up the two, okay? And tau is equal to 1 over the sampling frequency, okay? So actually this unit can be also, this dimensionless quantity can be also imagined as the ratio of the natural frequency and the sampling frequency, okay? Where so Fn in hertz, it's the natural frequency, and now the subscript n refers to the natural, okay? Natural frequency, and actually it is omega over 2 pi, okay? And Fs also in hertz. As before, it was the sampling frequency, and this S is the subscript, okay? Fs is the sampling frequency. It is 1 over tau, okay? So it will be already nice that actually what already can be predicted, that the problem, the main problem with all this force control stuff will be that it depends what we touch and what is the natural frequency what we touch. And it will be very important that what is the combination of the natural frequency and the sampling frequency. Okay? So, but funnily enough, again, the vibration which occurs, it is far from the natural frequency and from the sampling frequency, because it will oscillate like a Parkinson disease, only just a few hertz, okay? Far away from the natural frequency and the sampling frequency. And again, it's very difficult to imagine that this low frequency oscillation is actually caused by these high frequencies, because they can both in the range of hundreds of hertz, and in the meantime the resulting vibration will be only a few hertz, okay? But in the same way as we understood it in case of position control, this vibration frequency can be very low because of that natural logarithm of that characteristic multiplier. Okay, so let's try to start a little bit the calculation. I'm sorry, I will not. So it will be really too long. Even I have a lot of time here to give it, but I would also like to speak about the balancing and about the stabilization of the equilibrium. So I thought that tomorrow, the lecture will be continued tomorrow afternoon. So tomorrow afternoon we would finish this force control, and then next week, Tuesday, Wednesday, Thursday, we will still have 3 lectures for the balancing, for the stability problem, okay? So I will not do all the calculations in details, but I try to make it credible. So at some parts I will give only the results, but I hope that you will see that you will be able to imagine how it works. So you see, in this case the problem is that the right hand side is actually constant, piecewise constant, but the acceleration will not be constant because it will be just like a spring subjected to a piecewise constant force. Okay? Just like an oscillator subject to a piecewise constant force. So it will be like the case of the Coulomb friction in some sense, or the weight, when you have an oscillator and you have a system like this. So again, we have to use what we discussed already on the very first lecture. Okay? So if you want to solve this, solve it for each sampling interval with initial conditions with initial conditions xj and x prime j. Okay, so this is the initial velocity, initial position and initial velocity, and we should see. So we try to do the same. We would like to figure out what will be the value of it on, after one oscillation. Now, of course, again, it's somewhat intuitive, so I'm just thinking about how to explain that. Why don't I introduce a new notation now for this right-hand side? But we will just try solving it, and we will see that in this case, the discrete mapping could be constructed in a different way. So I just cannot say it algorithmically. So clearly, the general solution will look like, first, yeah, I don't know how to start it. Anyway, I will start with the general solution. So it's non-homogeneous general solution of the general solution of the non-homogeneous equation. The general solution of the non-homogeneous equation. It will look like x of t equals to x homogeneous t plus x particular t. Okay? Now, where x homogeneous t clearly comes from the simple oscillator, okay, where this would be the frequency of the oscillation. So this will go with C1 and C2. I think that's how I denote it. C1 times cosine omega tau capital T plus C2 times sine omega tau and capital T. Okay? And then C1 and C2 will come from the two initial conditions. And then the particular solution, since the right-hand side is constant, the particular solution will be constant, okay? And actually, it will be just simply 1 minus p times I don't want to tell, I don't think, yeah. It will be just 1 minus p times x at j minus 1, okay? I hope it is clear that, that this is the xpt is 1 minus, it's constant, 1 minus p times x at j minus 1, okay? And now the two things can be put together to get the general solution, okay? So you add this, it will be quite lengthy. To get the initial condition, you will also need x dot capital T. But when you do x dot capital T, then you will have xh dot T plus xp dot T. And xp dot T will be clearly identical to 0 because the derivative of the constant is 0. So it will be simply minus C1 times omega tau, sorry, it's prime, okay? These are all derivatives with respect to the dimensionless time, okay? So if you do differentiate it with respect to dimensionless time, it will be minus C1 omega t sine omega tau times capital T, and there will be a plus C2 times omega tau times cosine omega tau times capital T. I think I wrote it correctly, yeah? And now we will have to substitute xj and xj plus 1. So xj will be actually equal to, yeah, you substitute there j. So it will be C1 times cosine omega tau j, okay, plus C2 times sine omega tau j, and then and plus the particular, which is plus 1 minus p times x at j minus 1. Okay? It will look like that. And then x prime at j will be minus c1 omega tau sine of omega tau times j and plus c2 times omega times tau times cosine omega times tau times j. Okay? So this will be, these are the two equations which actually should be solved for C1 and C2. Okay? So, what's the time? I think it's just time because we started at 9 and with 2 minutes break we should stop here. Next time I will summarize briefly the steps of these things, okay? And because we spoke about so many things and there were a couple of things maybe I over-explained it. For example, this one was unnecessary, just made a confusion, okay? So next time I will try to briefly summarize it. Maybe I will not spell out all the notation and all the subscripts as detailed as I did today, but tomorrow morning I will summarize all these steps, and from here we will give what is the solution for C1 and C2. You see, it will be quite lengthy, but I would like to write it out as a, you know, you can give it in a matrix form, so it's very nice. The coefficients of C1, C2, there will be cosine omega tau j, then there will be sine omega tau j, then here on the lower left corner it will be minus omega tau sine omega tau j, and in the lower right corner it will be omega tau times cosine omega tau j, and this is multiplied by C1 and C2, and this will be equal to, on the other side, well, I don't have enough space to spell it out, but there will be this 1 minus p times x at j minus 1, and there will be this minus xj, okay? And tomorrow I will put it down again to make it clear, okay? And since the determinant of this matrix is just omega times tau, which is non-zero, you can always solve it for C1 and C2. And we will have a nice solution for C1 and C2. Nice, but very lengthy. And can you imagine, this C1 and C2 will have to be substituted back in here, okay? So for the first glance, again, you give up and you say that, oh, it has no sense to continue. And actually, if you try to do it with Maple and Mathematica, then it will start becoming longer and longer. But if you watch it, how you could simplify, and with Maple it's quite difficult to find it, that how to simplify it, but if you try to do it for yourself, or you write it out, then you recognize the simplification, and you will see that finally, again, we will be able to construct a relatively simple 3x3 matrix, and the stability of that will show us how the stability chart looks like. And the stability chart will be surprisingly complicated, okay? But still, so it's just to make you interested and also to come tomorrow, okay? Because tomorrow maybe there will be less videos, but the chart will be very exciting, okay? And again, we will have nice analytical closed form results for the maximum gains and for the minimum errors and everything like that. So, and also we will get conditions that what the ratio of the natural frequency and the sampling frequency could be, and what are the problems. It's not just simply when they agree that's bad, because you say that, oh, it's a kind of resonance. No, it will be more complicated. Anyway, thank you very much. See you tomorrow.